Welcome to my data questions in biology theory. The data questions are just like the practical. My audience and all the people who watch my videos, welcome to my data question in biology biology. I wanted to say practical because I'm used to practicals. But I'm also dealing with the data questions, guys. Remember, a data question is a question in paper 2, and it is compulsory. It's a compulsory question. And therefore, I've seen the need for me to polish the runners, or I share the knowledge I have with the biologists or anybody for that matter who will be touched by the content of this question. Remember, data question is something practical, and it is also a question which can affect you in a day-to-day life. So welcome to the channel, guys. So we open the data question by highlighting the information which is going to come in that question, because the question you have to ask yourself in this question is, why does a small rodent like a rat struggle to stay warm while a massive elephant or a massive animal like the elephant thrives in the same environment? The small animal is struggling. What about the bigger animal? So have you ever wondered why animals in different climates are have unique adaptations to survive? In this experiment, we will uncover the fascinating science behind how temperature affects living organisms. By observing how different insulating materials impact heat loss, you gain insights into animal physiology and discover practical applications for everyday life, like choosing the right clothing or insulating your home effectively. Very important. Just as cotton wool can insulate boiling tubes in our experiment, the fur and fat of mammals serve a similar purpose in the natural world. Let's explore these concepts together and see how they apply to our life. So, in an experiment to investigate a certain physiological process, a boiling tube labeled A and a test tube labeled B were covered with cotton wool. The two tubes were simultaneously filled with hot water and fitted with thermometers. The experiment setup was as in the diagram there. Okay, so you can see the thermometers, the test tube, the boiling tube, and the cotton wool. A is a boiling tube, B is a test tube. Temperature readings were taken at the start and after every 2 minutes for 20 minutes. The results are as shown in the table below. Using the same axis, draw graphs of temperature against time. Work out the rate of heat loss in the boiling tube labeled A and test tube labeled B between the 5th and 15th minutes. Account for the answers in B1 above. How does the explanation in B1 above apply to the elephant and the rat, the one we started with? State the role of the cotton wool in the experiment. Name two structures in mammals that play the role stated in C1 above. And then state three advantages of having constant body temperature in mammals. The experiment shows two tubes, A and B, and each filled with hot water and covered with cotton wool. The temperature is recorded at 2-minute intervals over a span of 20 minutes to observe cooling rates. Tube A represents a boiling tube with a test tube inside, which is meant to simulate a biological process or insulation mechanism. Tube B is a single test tube setup. Based on the temperature readings, tube A loses heat more slowly compared to tube B. Tube A starts at 60 degrees centigrade and drops to 46 degrees centigrade over 20 minutes, while tube B starts at 60 degrees centigrade but drops 30 degrees in the same period. This setup likely investigates the effect of insulation or other physical barriers represented by cotton wool and the test tube arrangement on heat loss, mimicking the regulation in biological systems such as mammals or organisms might conserve heat. Here are the steps for drawing the graphs of the temperature against time. Prepare the data. Collect the temperature and time data like the one provided in the experiment. Organize the data into columns, one for time independent variable and one for temperature dependent variable. Draw the axis. X-axis is horizontal. Label it as time in minutes because time is the independent variable. Y-axis or vertical, label it as temperature degrees centigrade because temperature is the dependent variable. Use appropriate scales for each axis based on your data range. The time scale should cover the full range of the minutes recorded, e.g. 0 to 20 minutes. The temperature should accommodate the highest and the lowest recorded temperatures, e.g. 30 degrees centigrade to 60 degrees centigrade. Mark the scales. Decide on uniform intervals for each axis. For example, on the x-axis, mark points at every 2 minutes. That is 0, 2, 4, 6. On the y-axis, mark points at every 5 degrees centigrade. 30, 35, 40, up to 60 degrees centigrade. Ensure the intervals are consistent and appropriately spaced for clear readability. Follow to the points. For each set of time and temperature data, locate the corresponding point on the graph. For example, if at 2 minutes the temperature is 59 degrees centigrade, find 2 on the x-axis and 59 on the y-axis, then mark a point where these meet. Do this for all data points. Draw the lines. After plotting the points, connect them with a smooth curve or straight line. If the data changes gradually, use a smooth curve to represent the trend. If the data changes more sharply, you can use straight lines between the points. Label the graph. If plotting more than one set of data for both boiling tube A and test tube B, use different colors or markers for each data set. Include a legend to indicate which line represents which data set. Boiling tube A in blue and test tube B in red. Give the graph an appropriate title such as temperature versus time for boiling tube A and test tube B. Check and interpret. Ensure all points are correctly plotted and connected. Interpret the trend. Does the temperature decrease steadily over time? Which data set cools faster? Example process. Step 1. You have time 024 up to 20 minutes and the temperature 60 degrees, 59, 57, etc. data. Step 2. Draw X and Y axis and label them with units. Mark appropriate scales on both axes. Step 4. Plot points such as 259, 459, 655 for tube A and 254, 450 for tube B. Step 4. Connect the points for each tube with smooth lines. Under title and legend or key to identify the tube A and tube B. By following these steps, you have a clear graph representing how the temperature changes over time for both tubes. So that is your graph. Your graph is there. Alright. That is your graph. You can see very clearly if the axes are reversed, allow only one mark for identity. If you draw two graphs, mark first, give maximum 3. Only one graph. E.g. for A, give 4.5 to 5. All right. Okay. You can see time, minutes, labeling the axis, have a mark. Scale there, you get a mark. Scale on y-axis, a mark. Have a mark for labeling the axis. Plotting, have a mark on each graph. Curve, have a mark on each graph. Identity, have a mark for each graph. Computer-generated graph. Computer-generated graph. Here is the graph of temperature against time for both boiling tube A and test tube B. The blue line represents the temperature change in boiling tube A, showing a more gradual decrease in temperature. The red line represents the temperature change in test tube B, which cools faster over the 20-minute period. The graph usually illustrates the difference in heat retention between the two setups. So there you are. That is the computer generated. Remember, the other one was drawn by hand by the examiner. Temperature versus time for boiling tube A and test tube B. You can see the legend there at the top. This is the legend which is blue and the other one is red. Boiling tube A, test tube B, and you can see how the curves are and the way the points are plotted. Temperature and time in minutes. Work out the rate of loss in the boiling tube record A and the test tube record B between the 5th and the 15th minute. The rate of heat loss between the 5th and the 15th minute is boiling tube A, that is 56 to 48 minus 48.5, which is 7.5 degrees centigrade. 7.5 degrees centigrade over 10 minutes gives you 0.75 degrees centigrade per minute. For test tube B is 48 minus 38, which is 14 degrees centigrade, and this gives you 14 over 10, which is 1.4 per minute, degrees centigrade per minute. Accept 1.4 degrees centigrade per minute. Accept a variation of 0.05, that is 1.35 or 1.45. This shows that test tube B loses heat faster than boiling tube A during this time period. Account for answers in B1 above. B has a larger surface area to volume ratio, making it lose heat to the surrounding faster. Accept the converse. A has a smaller surface area to volume ratio. Roman 2. A rat has a large surface area to volume ratio compared to an elephant, making the rat to lose heat at a faster rate than the elephant. Accept converse, that the elephant surface area volume ratio. Account for the answers in B1 above. The difference in the rate of heat loss between boiling tube A and test tube B can be explained by the experimental setup. Boiling tube A has a slower rate of heat loss, 0.3 degrees per minute, because it is better insulated. The presence of smaller test tube inside the boiling tube, along with cotton wool, provides extra insulation. This reduces the rate of heat transfer to surrounding environment, mimicking biological processes like thermoregulation in warm-blooded organisms. Test tube B, with a faster heat loss rate, 0.5 degrees centigrade per minute, lacks the additional insulation present in tube A. It has only a single layer of cotton wool around it, allowing more heat to escape to the environment. This setup demonstrates faster cooling, similar to what happens in organisms or systems with minimal insulation or heat conservation mechanisms. The key factor is the level of insulation in each tube, which slows down heat loss in tube A compared to B. How does the explanation B above apply to an elephant? The explanation of heat loss in boiling tube A and test tube B can be applied to differences in heat regulation between an elephant and a rat. Elephant. Elephants are large animals with a low surface area to volume ratio. This means that for their large body mass, they have relatively less surface area exposed to environment. Like boiling tube A, which has better insulation and a slower rate of heat loss, elephants lose heat more slowly because their large size helps retain body heat. Their thick skin and fat layers also act as insulation. Additionally, elephants have specialized features such as large ears that help dissipate heat when necessary, allowing them to regulate temperature more effectively in hot climates. Rat. Rats are small animals with a high surface area to volume ratio. For their smaller body mass, they have more surface area exposed to the environment, leading to faster loss. Similar to test tube B, which loses heat more quickly due to minimal insulation, rats lose heat more rapidly because their smaller size makes it difficult to retain body warmth. To compensate, rats need to generate more heat through higher metabolic rates, and they tend to seek shelter or huddle together in cold environments to minimize heat loss. In summary, just as the setup in the experiment shows different rates of heat loss due to insulation, elephants and rats experience varying heat retention and dissipation due to their size and surface area to volume ratio. Large animals like elephants lose heat slowly, while small animals like rats lose heat more quickly. State the role of cotton wool in this experiment to insulate against heat loss to surrounding, accept, prevent, minimize heat loss, reject, prevent loss of temperature. Names two structures in mammals that have the same law stated in see above. Subcutaneous fat or layer or adipose tissue, fur or hair. The role of cotton wool in these experiments will act as an insulating material, reducing heat loss from both the boiling tube A and the test tube B. By covering the tubes with cotton wool, the experiment simulates conditions that slow down the transfer of heat from the hot water inside the tubes to the surrounding air. This helps in demonstrating how insulation affects the rate of heat loss, similar to how animals use body fat, fur, or other mechanisms to retain heat in cold environments. In this context, cotton wool represents the insulating layers that slow down heat dissipation. The structures in mammals that play an insulating role similar to the cotton wool is fur or hair, acts as a thermal insulator by trapping air close to the skin, reducing heat loss from the body to the surrounding environment. Subcutaneous fat or fat layer, a layer of fat beneath the skin that serves as insulation by preventing heat from escaping the body, helping to maintain internal temperature. State advantages of having constant body temperature in mammals. They are active, are able to escape from predators, can survive in both cold and hot habitats. So having a constant body temperature in mammals known as homeothermy provides several advantages. Optimal enzyme function. Enzymes in mammals function best within a narrow range of temperature. Maintaining constant body temperature ensures biochemical reactions occur efficiently, supporting vital processes like digestion, respiration, and metabolism. Enhanced activity in various environments. Mammals can remain active in a wide range of external temperatures, whether in cold or hot environment, without becoming sluggish. This ability allows them to hunt, forage, or escape predators in diverse climates. Stable internal environment. Constant body temperature helps maintain stable conditions for bodily functions such as proper gas exchange in the lungs and efficient nutrient transport by the circulatory system. Improved survival. By regulating their body temperature, mammals can survive in extreme environments, e.g. cold or hot climates, giving them broader or geographical range compared to animals that rely on external temperature to regulate their body heat. Sustained high metabolic rate. Constant body temperature allows mammals to maintain high metabolic rate, which is essential for activities requiring large amounts of energy such as running, hunting, and reproduction. Application to real-life situations. The principle learned from this experiment about heat retention and loss have several real-life applications, particularly in areas like biology, engineering, and everyday human practices. Animal adaptations. The experiment models how animals, especially mammals, regulate their body temperature. Understanding how insulation like fur or fat slows down heat loss helps us explain why animals in cold climates, e.g. polar bears, have thicker fur or blubber, while animals in hot climates, e.g. camels, have adaptations to prevent overheating. It also demonstrates why smaller animals like rodents lose heat faster and tend to have higher metabolic rates or engage in behaviors like handling to conserve warmth. Clothing for humans. In cold weather, people wear insulating materials such as wool or synthetic fibers similar to the cotton in the experiment to reduce heat loss from their bodies and stay warm. Layering clothing in winter works on the same principle of trapping air and minimizing heat dissipation. Building and home insulation. The concept of insulation is applied in construction to conserve energy, just as the cotton wool slows heat loss in the experiment. Materials like fiberglass or foam are used to insulate buildings, keeping them warm in winter and cool in summer, reducing the need for heating and air conditioning. Thermos flasks and coolers. Insulated containers such as thermos flasks or coolers work on the same principle as the cotton wool experiment. These containers are designed to minimize heat exchange, keeping liquids hot or cold for extended periods by reducing heat loss or gain, similar to how the cotton wool slows down heat loss from boiling tubes. Medical applications. Understanding heat loss is critical in medical settings such as caring for premature infants who may struggle to maintain their body temperature. Incubators are designed to regulate their temperature using principles of insulation to prevent excessive heat loss. Energy conservation. This principle is also applied in energy conservation strategies such as designing energy-efficient homes or vehicles. By improving insulation, less energy is required to maintain comfortable temperatures, reducing energy consumption and costs. In summary, the lessons on heat retention and loss have wide-ranging applications from understanding animal biology to improving human comfort and energy efficiency in daily life. My special thanks to ChatGPT, an AI language model developed by OpenAI, for providing assistance with creating, polishing my content for this video. I also acknowledge that teamwork spirit we had with my fellow teachers during that time of my teaching life. Goodbye and see you in my next videos of this type, that is biology data questions. Goodbye, and may you subscribe to my channel.